Picture this. You flick on a lamp. The light hits your eye. Simple, right? Wrong. Because according to Feynman, that beam of light just took every possible path through the universe to get there. Every detour, every loop, every path that bends through the moon and back, all at once. Now the bloke who figured this out, you've probably heard of. Feynman, quantum electrodynamics, the bongo drums, the safe cracking at Los Alamos, the dude who taught physics like it was a stand-up routine. But there's one theory of his that quietly rewrote how we understand reality. And almost nobody outside of physics labs talks about it. Stick with me, because by the end of this video, you're going to look at your morning coffee a bit differently. Fair warning, so picture this. It's 1948. The world's still picking up the pieces after the war. Quantum mechanics is in a bit of a mess, and physicists are scratching their heads trying to make sense of how particles actually behave. The old way, Schrödinger's wave equation, works, but it's clunky. Like trying to drive a manual ute with no clutch. Enter Feynman, 29 years old, cocky, brilliant, allergic to convention. And instead of asking what equation describes this particle, he asks something completely different. He asks, what if the particle doesn't pick a path at all? What if it takes all of them? Now hang on, because this sounds insane. You throw a tennis ball at a wall, it goes in a straight line, bounces off, comes back, you catch it. One path, one ball, one outcome. That's how the world works, mate. But down at the quantum level, electrons, photons, the tiny stuff that builds you, your phone, your toast. Feynman said no. An electron going from A to B doesn't just take the straight line. It takes the curve, the zigzag, the loop, the path that goes to the bloody moon and back. All of them, simultaneously. And before you go, mate, that's just maths. That's not real. Here's the kicker. We've tested this. The double-slit experiment, which you might have seen on a documentary while half asleep on the couch, that's basically a ticket stub for path integrals. Fire one electron at two slits, and somehow it goes through both. Not because it splits in half, because it's taking every possible route, and they're all interfering with each other to produce the pattern you see on the screen. This idea has a name, the path integral formulation, or, if you want to sound clever at a barbecue, the sum over histories. And the genius bit, the bit that makes physicists go a bit weak at the knees, is the maths Feynman invented to handle it. Each path gets a little number attached to it, kind of like a phase on a clock face. Most of the wild paths cancel each other out. The boring straight line, the one your tennis ball takes, that's the one that survives, because all its neighbours add up nicely. So the reason your tennis ball goes straight isn't because it can't take detours. It's because all the detours cancel themselves out. Right? Real life example. You're standing in front of a mirror. Light bounces off your face, hits the glass, comes back to your eye. Easy. You learnt that in primary school. But here's what they didn't tell you. According to Feynman, that light is also bouncing off every other point on the mirror, and every other point in the room, and every other point in the universe. It's just that all those paths cancel except the one that obeys angle of incidence equals angle of reflection. The mirror's not picking the right path. The universe is just averaging out all the wrong ones until only the right one's left standing. And here's where it gets properly weird. You ready? This isn't just a clever way to do quantum mechanics. The path integral has slowly, quietly taken over physics. Quantum field theory, built on path integrals. Particle physics, every prediction the Large Hadron Collider makes, every Higgs boson signature, every quark interaction. Path integrals, string theory, loop quantum gravity, even the speculative attempts to combine gravity and quantum mechanics into one big, elegant equation. All sitting on Feynman's idea. This thing he came up with as a young bloke in his 20s has become the most powerful calculation tool in the history of physics. And most people have never heard of it. But here's the bit that genuinely keeps physicists up at night. If the path integral is right, if particles really do explore every possible history, then in some deep mathematical sense, the universe you're sitting in right now is the average of every universe that could have happened. Every coffee you didn't spill, every train you missed, every conversation you almost had. Every alternate version of this exact afternoon. They're not just what-ifs, they're contributions. Faint, mostly cancelled out contributions, but contributions to the path that became real. Reality, in Feynman's view, isn't a single line drawn from past to future. It's a chorus, billions of possibilities humming over the top of each other. And what we call existence is just the loudest note that survived the cancellation. Pretty wild for a theory most people skip past, eh? If your brain's a little bit fried right now, that's the goal. Smash the like button if Feynman just earned a bit more respect from you, drop a comment with the weirdest physics fact you know, and subscribe to Physics Forge. We're going deep on this stuff every week. No fluff, no jargon, just the good bits. Cheers for hanging around. Catch you in the next one.